Hi everyone, thank you for tuning in. My name is Roei, and this talk is titled Depth D Threshold Circuits versus Depth D+1 and/or trees. And it's a joint work with Pooya Hatami, William Hoza, and Avishay. And let me first state the main result very briefly and upfront in a way that experts can get, and then later on I'm going to present things in a more orderly way. So the main theorem in this work is that there is a function that's hard for TC0 circuits of depth D and superlinear size, but is computable, this is the upper bound, by uniform AC0 of depth D+1, just one more layer. So it's a circuit lower bound for TC0 of superlinear size, where the upper bound is AC0 with one more layer. And the main technical tool in proving this result, the main technical lemma in this work, is that the random projection procedure of Hastad, Rossmann, Servadio, and Tan, when parameterized a bit differently, simplifies every TC0 circuit of superlinear size. Let's start with the background. I want to define linear threshold circuits, or in short, LTF circuits. And these are circuits computing Boolean functions. So here is a function from 0, 1 to the n to 0, 1. They're directed graphs, cyclic. At the bottom, we have the inputs, x1 up to xn. Above the inputs, there are layers. Each layer has gates. Each gate can compute an arbitrary linear threshold function. So the gate takes a weighted sum of the gates below it, checks whether or not it exceeds some predetermined thresholds, and says yes or no accordingly. The computation propagates to the top. The top gate computes another linear threshold function of the gates below it, says yes or no, and that's the output. This is how the circuit computes a Boolean function. We measure the size of the circuit as the number of wires in it, and the depth of the circuit as the number of layers above the inputs. So for example, this is a depth 3 circuit. And the class TC0 consists of all languages decidable by families of linear threshold circuits of polynomial size and constant depth. So we're talking about non-uniform families. For every input length n, there can be a different circuit, C sub n, computing the function at this input length, and there isn't necessarily a finite size description of the entire family. And the class TC0, we defined it right now using linear threshold gates as the gate basis, but it has several equivalent definitions. We can replace linear threshold gates with simple majority gates. We've known that since the early 90s. So we can weaken the gate basis. And we can also replace linear threshold gates with arbitrary symmetric gates, which are stronger than simple majority gates. But these transformations have a polynomial size overhead, and we're going to care about precise size bounds, so we're sticking with the definition that uses specifically linear threshold gates. And here's an open problem. Show an explicit function, say a function in NP, that's hard for TC0. We don't know how to solve this, and in fact, we seem quite far away. We don't even know how to show a function in exp to the NP that's hard for TC0. And this is an important open problem. It has several motivations. First, it's a necessary step towards separating P from NP in the circuit lower bounds program. So if we want to show that NP is hard for P over poly, we first need to show that NP or X to the NP is hard for TC0. It's also a necessary step towards showing that PPP equals P in the circuit lower bound program. So if we want to show that E is hard for exponential size circuits and get PRGs, we first need to show a circuit lower bound for TC0. And another motivation comes from the world of neural networks. So as you might have noticed, linear threshold circuits can be viewed as a very simplistic model of a neural network. They have been viewed so even in the early days, in the 1960s. It's one original motivation for studying this model. So studying lower bounds for TC0 can be viewed as studying the limitations of simplistic models of neural networks. And what do we know? So here's a context slide. It's a standard slide with like a very rough state of circuit lower bounds. So we have the class AC0, a simple class, consists of constant depth circuits with and or not gates, and we've known since the 80s that it fails to compute the parity function, the mod P function. And when you increase the gate basis and allow it to compute parity or mod P, we've known since the late 80s that it fails to compute the majority function. And if you allow it to compute mod M for any integer M, you get the class ACC0, and we've known in the last decade that it fails to compute non-deterministic first exponential time, and now we know that it fails to compute non-deterministic quasi-polynomial time. And it's conjectured to even fail to compute the majority function. So now let's add the majority function to this gate basis, and we obtain the class that we currently focus on in this talk, TC0. All right, so what do we know about circuit lower bounds for TC0? Let's start with a fixed small depth, specifically depth 2. These are LTF circuits. So it's LTF at the top, then a layer of LTFs, then the inputs. And Kane and Williams showed not too long ago that LTF circuits of size less than n to the 2 to the half fail to compute the generalized Andreev's function. So we have fixed polynomial size circuit lower bounds for LTF circuits. We also know that circuit analysis of depth 2 threshold circuits would be enough to get lower bounds for LTF circuits of arbitrarily large polynomial size. So if you can approximate the acceptance probability of a circuit with just 2 layers, you get lower bounds for LTF circuits. In fact, it suffices to approximate the acceptance probability of circuits with simple majority gates. And this is a promising approach since we know of strong exponential circuit lower bounds for majority of majority gates since the 80s. If we can analyze them and approximate their acceptance probability by a non-trivial algorithm, we'd get nx lower bounds for LTF circuits of polynomial size. However, so far, this is by Chen and Williams, so far no one has been able to actually materialize this and construct such an algorithm. So it's still open whether or not LTF circuits of polynomial size can compute all of x to the np, which sounds ridiculous, but we don't know how to rule it out. Okay, so we seem to be stuck even at depth 2, but let's be brave and go to arbitrarily large constant depth. So what do we know when the depth d is an arbitrarily large constant? When since the late 90s, we've known, it was proved by Impagliazzo, Paturi, and Sachs, that such circuits of superlinear size fail to compute certain functions, the parity function or Andreev's function. And recently, Chen, Santanam, and Srinivasan showed that this lower bound even holds on average over the uniform distribution. And specifically, these are circuits of size n to the 1 plus a tiny constant that decays exponentially with the depth. So it's c to the minus t, where d is the depth. And in recent results, we have unconditional algorithms for such circuits. So a quantified de-randomization algorithm, which is a weak type of de-randomization algorithm, and a non-trivial pseudo-random generator, a PRG, for LTF circuits of this depth and size. So depth d size n to the 1 plus c to the minus d, where c is some constant. This is a result by Tell and by the current set of authors in a previous work. And we also note that the constant c here actually matters a lot. So improving the known lower bounds for NC1 complete functions from the 90s, or the known quantified de-randomization algorithm that I just mentioned, to work with a smaller constant c, so n to the 1 plus c to the minus d, where c is smaller, would be enough to get lower bounds for all of TC0, for arbitrarily large polynomial size, separating nx from TC0. However, analogously to the case of depth 2 circuits, this hasn't been materialized so far, and we don't know how to do it. Okay, so given that we're currently stuck and don't know how to prove lower bounds for larger circuits, let's look at another path to make progress. Let's take a look at some results that I mentioned. Parity is hard for AC0, majority is hard for AC0 parity, parity is hard for TC0 of superlinear size, and another well-known result, Andreev's function is hard for formulas of subcubic size. And let's look at the hard functions themselves. Parity, majority, Andreev. These are functions computable in NC1. Can we show lower bounds for these circuit classes where the function is even simpler in the sense that it can be computed in a weaker complexity class? Well, in an exciting line of works from the last decade, it turns out that in many cases, the answer is yes. Let's start with AC0. So since the 80s, we've known that AC0 of depth d plus 1 is hard for AC0 of depth d. That was by Hastad, and recently, Hastad, Rossmann, Servedio, and Tan showed that this even holds on average. So it's an average case lower bound. And as for AC0 parity, well, O'Donnell, Weimer, and Amano, as observed in subsequent work, showed that there is a lower bound for AC0 parity that's computable in AC0 with just one more layer of depth. So AC0 of depth D plus 1 is hard for AC0 parity. And very recently, Filmus, Meir, and Tal showed that even for formulas, the situation is similar. There's a function in AC0 that's hard for formulas of subcubic size. And let me just mention, whenever I say computable in AC0, I mean uniform AC0, right? The point here is showing uniform lower bounds for non-uniform circuits. And of course, this leaves one outlier, TC0 circuits, and this is going to be the focus of this work. Our main result addresses precisely this gap. Let me state it now. So fix D. D can be a constant, and it can even be super constant, up to something that's bounded from log n. And fix a parameter gamma, which is something that decays exponentially with D. We're going to care about TC0 circuits of size n to the 1 plus gamma. So we show that there is a function L sub D plus 1, computable by uniform AC0 of depth D plus 1. In fact, it's read once AC0 formulas, such that every LTF circuit C of depth D and size n to the 1 plus gamma fails to compute this function. In fact, it fails to compute it even on average. It succeeds on at most half plus n to the minus gamma of the inputs. And a few comments are in order here. So let's look at the upper bound, AC0 of depth D plus 1. So the hard function requires just one more layer on top of the TC0 circuit. And it's a read once formula, so it's of linear size. So it's even computable with less size, right? N, O of n, instead of n to the 1 plus gamma. The function is even monotone. It's just a read once and or tree over the input. Sipser's function just parameterized differently. The second comment is that the lower bound is in fact close to optimal for this particular function. So the lower bound is that every TC0 circuit of superlinear size and depth T computes the function at most half plus n to the minus gamma of the inputs. But there is unconditionally a near matching upper bound of half plus log n over n, since the function is like a read once monotone formula, etc. So like unconditionally, it can be approximated by a single variable with this success. Okay, now let me mention, I call it a corollary, but it's just another perspective on this result, and it's the impossibility of depth reduction using LTF gates. So here's a challenge, and don't try it because we proved it's impossible. So I give you an AC0 circuit of depth D plus 1 and of linear size, so linearly many wires, and I ask you to reduce its depth by a single layer using LTF gates. And even as a gift, you're allowed to use some additional wires, n to the 1 plus gamma wires. And the main theorem says that this is impossible to do. Even if the AC0 circuit is a read once monotone formula, just an AND OR tree, you cannot reduce its depth in general using LTF gates. And it's a non-obvious statement. Like intuitively, why shouldn't it be doable? We're only being asked to shortcut one layer of depth, and we're allowed LTF gates, which are quite strong. And also, we can compare this with a known unconditional upper bound. So if we're allowed quasi-polynomially many gates, we can do it. We can reduce the depth. In fact, we can reduce it from any constant depth to just depth 3. This is a result of Allender from the late 80s. However, the main theorem says that if the allowed size is just n to the 1 plus gamma wires, we can't reduce the depth even just by one layer. Okay, so this is the perspective of the impossibility of depth reduction for AC0 with LTF. And another result, this is a complementary result to the main theorem, belongs to the perspective of hardness magnification. This line of works from the recent decade, focusing on something that's coined hardness magnification. And informally, what's going on here is that for this particular function, L sub D plus 1, to show a polynomial lower bound of n to the k, it suffices to show a superlinear lower bound of n to the 1 plus gamma prime, where gamma prime is just slightly larger than gamma. Right, so we already know a lower bound of n to the 1 plus gamma for this function, and this result says that improving the lower bound to n plus 1 to n to the 1 plus gamma prime, where gamma prime is slightly larger, would be enough to get a lower bound of n to the k, a polynomial lower bound. This is something that we don't know, of course, for TC0 for any function in x to the np. And gamma prime, again, decays exponentially with the depth. It's like k times 10 to the minus d. And this is similar to what happened in Chantel. The constant c, the base of the exponent in the decay, actually matters a lot, turns out. And let me state this more formally. So we're stating the contrapositive. If there is an upper bound on L that is a polynomial, then there is a superlinear upper bound, much better upper bound on L. So fix an integer d0 and assume that L d0 plus 1 is computable by LTF circuits of depth d and size n to the k. Then for a larger depth d, L sub d plus 1 is computable by LTF circuits of depth d and superlinear size n to the 1 plus something that decays exponentially with d times some polylog factors. In the technical part of the talk, I'm going to explain our techniques a bit at a high level. My goal is to give a taste, some statements and explanations rather than full technical details. So let's start by recalling the classical technique of random restrictions. So a restriction procedure is a procedure in which we fix some of the input variables to values in 0 or 1, and we analyze what happens to the circuit after we fix these input variables. And we want to argue that the hard function survives after this fixing, after the restriction, whereas the circuit simplifies under the restriction. And since there is a difference in behavior between the hard function and the circuit, it cannot be that the circuit computed the hard function, and we get our lower bound. For example, maybe we want to argue that the hard function is unbiased over the subcube of living variables after the restriction, whereas the circuit is constant over this subcube, which means that the circuit couldn't have computed the hard function. Okay, and our high-level plan for analysis is very similar to Hastad, Rossmann, Servadio, and Tan. We're going to define a specific hard function L, the function from the main theorem, and tailor a restriction procedure that's custom-made, tailored to this particular L. The second step is to show that L survives the restriction procedure. You shouldn't be shocked by this, right? Because we tailor the restriction procedure specifically to L to keep it such that it will survive. And the main part of the work, which is essentially the entire paper, is to show that any LTF circuit simplifies under this restriction procedure. Okay, let's start by describing this L, the hard function. As I mentioned, it's just a read once and or tree. And it's very similar to the one in HRST, except that it's parameterized differently. The fan-ins in the and or tree are increasing as we go from bottom to top. So in the first layer, the fan-ins are logarithmic. It's epsilon log n for a tiny epsilon that depends on d. It increases exponentially in the second level. Suddenly the fan-in is n to the epsilon. And from then on, it increases polynomially by some power. So the fan-in the third level is f2 to the 100. The fan-in in the fourth level is f3 to the 100. And so on. After these steps, it would be 100 to the d in the power. And the restriction procedure that we use is, again, a variant of the original restriction procedure of HRST, which they call a projection procedure. It's, as usual, a sequence of restrictions, row 1 up to row d, one corresponding to each layer. But the restrictions are really not IID uniform, each of them by itself. They don't look anywhere near uniform. Each restriction by itself assigns values, 0, 1 values, in a highly biased way, either biased towards 1 or biased towards 0, and it assigns them in a way that has a lot of correlations between the variables. It's not that each variable gets an assignment independently of all others. And this is done in order to meet two conflicting goals, right? They want to show that the and or tree survives under this restriction, but they also want to show that the composition of row 1 up to row d is uniform enough. For example, when composing all of them, maybe with an additional last one, you get exactly the uniform distribution. This is to get an average case lower bound. And of course, you want to show that when applying this to, in their case, an AC0 circuit of depth d, then it's killed, right? It simplifies. In our case, it will be a TC0 circuit of depth d. And let me now just describe the projection procedure. You're not supposed to be convinced that these goals are met, but I do want you to understand at least how it looks like. So again, it's row 1 up to row d. There are d iterations, and in each iteration, we partition variables into blocks, where each block consists of all variables feeding into a gate at the ith layer. So in the first iteration, like each block is all the variables that feed into a gate in the first layer. And in the next iteration, it's all the variables that feed into gates that feed into a gate in the second layer, and so on and so forth. And for simplicity, let's describe what happens when the iteration corresponds to a layer of AND gates. And there is independence between blocks. So for each block independently, There are two cases, a case where we fix all the variables in the block and the case where we keep some of them alive. In the case where we fix the variables feeding into the block, we fix them in a highly biased way. So it's a it's like IID Bernoulli that's biased towards 1. Why is it biased towards 1? Well, we want to fix some biases from previous iterations because we want everything to compose to the uniform distribution in the end. But why is it almost IID instead of IID? Well, if everything will be fixed to 1, then we're going to kill not only the AND gate, but also the OR gate above it. And we want to avoid this. This is bad. So we artificially decrease the probability that we're getting the all 1 assignment in the block. Now, in the second case, we want to keep a small subset of variables alive. But in this case, also, we fix all the rest of the variables to 1, right? Because otherwise, the AND gate will be killed. And we don't want that to happen. We want to keep things alive there. So we choose some small subset of variables, we keep them alive, fix the rest of the block to 1. And the reason why it's called a projection is that in the next step, we're going to treat all the live variables in the block together, right, as one big variable. So we're going to fix all of them in the next iterations to 0 together or to 1 together or to keep them alive together. But really, we're going to be thinking of them as one big variable in next iterations. So as in the terminology of HRST, we're projecting this small subset into a new big variable. And the next iteration is going to be over a new set of variables where each variable represents a block. In this paper, we're using the same thing. We are describing it using an alternative equivalent definition, which is actually the definition that I just gave in the previous slide. This definition is more convenient for us to work with when we analyze TC0. And in case you don't like TC0, you're not interested in it, but you like the HRST projection procedure, I suggest you take a look at this equivalent definition. It might be nicer for you to work with for your purposes. And one difference is that from HRST is that our restrictions become more aggressive with time. So row I plus 1 is going to kill more variables than row I. We use this because it facilitates our argument that the LTF circuit simplifies. It's easier to argue that LTF circuits simplify with increasingly aggressive restrictions. And this is the reason why we use an AND/OR tree with increasing fan-ins to match these more and more aggressive projections. Nevertheless, still, the proof that the AND/OR tree with increasing fan-ins survive these increasingly aggressive restrictions is essentially the same as in HRST, it's just different parameters. This is not a big contribution of this paper, right? It's just replicating the original work. So we met our first goal, we defined the hard function, we defined the restriction procedure, in fact, the projection procedure, and we showed, like in HRST, that the AND/OR tree survives. As I mentioned, all of this paper is devoted to the third goal of showing that the LTF circuit simplifies. The main lemma is this. So consider the following distribution. Apply the projection procedure, and then assign IID biased Bernoulli values to the living variables with a suitable bias. Then, for any LTF circuit of depth d and size n to the 1 plus gamma, with high probability it simplifies. So with high probability over choice of restrictions, rho, there is a constant such that the circuit evaluates to this constant with a very high probability over x conditioned on this rho. Okay, so the circuit is essentially constant under the restriction. And moreover, x is the uniform distribution. As in HRST, we're shooting for an average case lower bound. And as I mentioned, the AND/OR tree survives. So under this, with exactly the same definition of x, the AND/OR tree is unbiased. It's very close to a half. Since the AND/OR tree is unbiased and the circuit is essentially constant, we get an average case lower bound. The circuit doesn't do much better than a random guess in computing the hard function. And the proof of this lemma has 3 parts. I'm just going to give highlights of these 3 parts. First, we're arguing that the projection procedure, each row I, simplifies any single LTF, a single linear threshold function. This is easy to show when the threshold function is a simple majority and row I is just an IID biased restriction. Now, the extension to arbitrary linear threshold function is also not difficult because it uses a structure versus randomness argument that has been well known in the last decade. It first appeared in a work of Servadio. But the extension to random projections when there are correlations and we merge things, is more challenging and it requires a lot of work. And moreover, the parameter, but we do prove this. It is nevertheless true for the random projection procedure, but the parameters are surprisingly subtle. The projection procedure that is used to keep the end-or tree alive happens to match what is needed for this particular proof that any LTF simplifies. The next step is to argue that the procedure simplifies a layer of LTFs simultaneously. It doesn't follow by a simple union bound. It relies on the fact that the circuit has a few wires. And we're going to argue that any TC0 circuit of depth D simplifies to a shallow decision tree with TC0 circuits of depth D-1 at its leaves. And this is actually not a difficult part. The argument follows known techniques. The known techniques carry easily to the setting of random projections. The techniques come from the work of Chen, Santanam, and Srinivasan. And the third part is to argue that the procedure simplifies a decision tree with LTF circuits at its leaves, right? Because after one restriction, we get a shallow decision tree with LTF circuits at its leaves, and we want to argue that the procedure simplifies this model. And this is a challenging part, because when we analyze it, we want to argue what happens in every leaf, and whatever happens in a leaf is conditioned on the event that we reach this leaf. And conditioning on the event that we reach the leaf introduces correlations between variables, because we're using these projections that have blockwise correlations. To meet this challenge and handling with high probability, we show that with high probability we can modify the decision tree such that even conditioning on reaching a leaf, the procedure simplifies any LTF and any layer. This is a subtle part and technical part of the argument. It requires proving stronger claims on everything that I just mentioned. And in case you're interested, see the paper. We took care to explain this part slowly. All right, let me conclude by mentioning again the takeaways and suggesting some open problems. So we prove a new lower bound for LTF circuits of superlinear size, showing that they fail to compute even a simple AND/OR tree, AC0, with just one more layer of depth. Another way to look at it is that we show the impossibility of depth reduction of AC0 circuit, even just by one layer when we're giving LTF gates. And the technical point here is showing that random projections, like in HRST, can simplify LTF circuits. This is a technical contribution. It wasn't known before how to analyze LTF circuits under projections, and it might find more applications. So here are a few open problems that might be tractable. First, can we improve the average case bound, right? The average case advantage. We show the lower bound of half plus n to the minus 0.001 for L. Can we get a better lower bound for L? Half plus 1 over n to the 0.99? Or can we ditch L and get another AC0 function, get a better lower bound? Say half plus something that is inverse quasi-polynomial. A second challenge is extending these results from linear threshold circuits to low-degree polynomial threshold circuits. And by the way, even our previous work in which we constructed a PRG for linear threshold circuits, the same open problem holds there. Can we get a PRG for low-degree polynomial threshold circuits? And the third, more technical open problem, maybe more open-ended, is to see if there are more applications of random projections to LTF circuits, now that we know that it's possible to analyze how LTF circuits behave under these random projections. In case you're interested, some places to head next and to find additional materials, the full paper is on ECCC, it's available. There are a lot of explanations. The current slides that you just saw are available on my websites. More detailed slide with more technical detail and explanations and with lovely drawings of pigs are available on Williams Hoza's website. Highly recommended. And please feel free to contact any of us with any questions or comments that you may have. Thank you very much for listening.